today we are going to be working on elementary row operations, but before we get into that, we have some groundwork we need to be laying. So first of all, I want us to just think back to why we're taking this class, why we're learning linear algebra, and remember that it's because we want to make our lives so much easier. So if we approach a linear system of equations like this in one of our fields, we're not like, oh my gosh, how do I solve this using substitution? Or do I really want to graph all those three planes? Instead, we're going to be using matrices and harnessing their magical powers in order to quickly and easily find a solution for x, y, and z that satisfies all of these equations simultaneously. So that is our main goal. So elementary row operations is what's going to be there to help us along the way to solve the mystery as to what x, y, and z are. But before we can use our elementary row operations, we need to figure out how we can represent this linear system using matrices. So with that, we are going to introduce one of our most important things, and that is matrix vector form. As the name implies, we are going to be finding a matrix and a vector that will help us represent this linear system of equations. So what we can do is we can take our three equations and pull the coefficients off of them. So remember, matrices are ways of storing data. So we can store here in our first column, or first row, all of the coefficients of our first equation. We can use the second row to store all of the coefficients on the left side of our second equation. And then finally, we can use our third row to represent the coefficients on the third equation there. Okay, so now we have all of our coefficients here. Then if you recall, this column will now represent all of our x's. So you see, oh look, there's all of our x values. This is where it's really important to point out that when we are writing our linear system of equations, it's so important to make sure that they're all lined up. So when you're quickly going through and making this matrix, you're not like, oh no, I accidentally threw a z in the y column. Oh no, my whole matrix is messed up. This way we can just quickly, easily be like, okay, so then all of our y's are 3, 2, 2. So we have 3 y's in our first equation, 2 y's in our second equation, and 2 y's in our third equation. So then lastly, as you can probably expect, our third column represents all of the z's. So now we need a vector that we can multiply this matrix by to represent our linear system of equations. And this is just going to be x, y, and z. So you can kind of use your own knowledge of matrix multiplication to see how this works out to represent our three equations here. So all you would have to do is multiply, okay, 5 times x is 5x, 3 times y is 3y, and negative 2 times z is negative 2z. Think, okay, where have we seen this before? Right up there. So see, okay, so this equals negative 4. So, I wonder where we can use this information at. So we have to have this equal to something, right? And we still have all of these to handle. So then we can see, using this knowledge, that means that negative 4 is going to be stored in our first row of our product there. We know that if 5 times x plus 3 times y plus 2 times z, negative 2 times z equals negative 4, that would be the corresponding entry of where we would have stored this in our product. So then we are in business here. So now, this is called our matrix vector form. And this matrix here is called our coefficient matrix, and we represent it using a capital A typically. And then our second vector here, which brings us to the matrix vector form, is represented with an x and the vector notation of a half arrow on top. And this is going to be our variable vector. And x is a classic variable that's probably the most common variable that we use. So that kind of will remind us, okay, so this is going to be all the variables in our linear system of equations. And then we represent this as B with the vector notation, and this is just going to be our right side. So it's on the right side of our matrix vector form, and that represents all of our right side of the equations in our linear system. So this is matrix vector form, and now we are going to use matrix vector form, and we are going to use that to put ourselves in augmented matrix. Augmented matrix is what we're going to be able to use with our elementary row operations. So all we do for our augmented matrix is we take our coefficient matrix here and we augment it, or draw this vertical line to combine our coefficient matrix with the right side vector, which is negative 4, 0, 1, and this is our augmented matrix. So you'll see it has the form. So this is our augmented matrix. So this is the matrix that we are going to be using for all of our elementary row operations. So now we're going to transition in to finding x, y, and z using our elementary row operations. So now we are ready to introduce our three friends of elementary row operations, which are multiply any row by a constant as our first friend. Our second friend is interchange any two rows. And then our third operation is multiply any row by a constant and add it to another row. So these are the three tools that we can use to solve the mystery as to what x, y, and z are. So let's get to know each one of these tools a little bit more. If we want to multiply any row by a constant, let's say we wanted to take row 2. We wanted to multiply it by 1/2, because perhaps we want all ones here in the second row. And we're going to store that back into row 2. So when we are doing our elementary row operations, it's so important that we keep track of every single row operation that we're doing and clearly label what one we are doing. So this notation here says that we're taking our constant 1/2, multiplying it by row 2, and that is being stored in row 2 in our next matrix. So if we go ahead and write our new matrix here, we're not doing anything with our first row or second row, so we can just copy those down without any issue. But then we are multiplying our whole second row here by 1/2. So we have 2 times 1/2 is 1, so we're storing it back in row 2. 2 times 1/2, 1, 2 times 1/2, 1, and then 0 times 1/2 is 0. So this is our new row after we've performed this elementary row operation. So we can see these two matrices do not look the same. So why were we able to just go ahead and multiply that row by 1/2? Remember that this matrix, our augmented matrix here, is representing this linear system of equations. So if we look here at our second equation, if we were not even think about matrices, and if I were just to be like, okay, so multiply both sides by 1/2, you'd be like, okay, yeah, and then you would get x plus y plus z equals 0. So that's actually what we have represented here, x plus y plus z equals 0. So we haven't changed anything about the integrity of this linear system, which is the most important thing to remember about elementary row operations, is that it doesn't affect the integrity of our linear system at all. All we're doing is manipulating it, trying to find the answer, but we're not changing anything about the linear system at its core. So that's really cool that we can just use all these cool new tools to try and solve our linear system. So now let's get to know our second operation here of interchanging any two rows. So let's say we wanted to interchange rows 1 and 2. We're denoting this with a R1 double arrow row 2, because row 2 is becoming row 1. It's being stored in row 1, and row 1 is being stored in row 2, or we're switching those two. So then if we look here, we're not doing anything to the third row, so we'll just keep that the same. But 2 is a little too close for my comfort. But row 2 here is going to get stored in row 1. So we'll just copy row 1 or row 2 into row 1. And then row 1 is going to be stored in row 2. So we just copy that right on in here. So there we see we have just performed our second elementary row operation where we've interchanged these 2 rows. Before we get to our third friend, let's think, why can't we just switch any 2 rows? Once again, these 2 matrices do not look the same. If we look at our original linear system of equations, if I were to write that with maybe the 5x plus 3y minus 2z equals -4, and then I would write maybe the third equation next, and then the second equation, does that change anything about our linear system? Would that have any effect on our solution? No, so then that's totally legal, so that's why we are able to go ahead and interchange any 2 rows, because that's just what we did here. We just wrote the second equation as our first row and our first equation as our second row. So we haven't changed anything about the integrity of our linear system using our elementary row operations. So now for our third and final elementary row operation, this is multiplying any row by a constant and adding it to another row. So let's say perhaps we wanted to take row 3 and we wanted this to be a 0. So what we could do is we could take -3 times row 1 and add it to row 3 and store that right on in row 3. So actually we're just gonna, so we don't run out of space here, we're gonna write this right here. Right down here. So we're only changing row 3 because it's the only thing on this side of the arrow. Also with elementary row operations, we just change 1 row at a time. These other rows are unaffected. So row 1, even though we're multiplying it by -3 and adding it to row 3, there's nothing being changed about row 1. So we'll see that reflected here as we just have 1, 1, 1 as our row here. It's going to stay exactly the same. We're changing nothing about that. Once again, we're keeping our row 2 the same. And you'll notice that even though we had done this interchanging here, I'm still referring to the second row in the current matrix that we're working with as row 2. That's just kind of simplicity, so we're not being like, okay, wait, because you're not always going to have color coordination in order to see. So I'm using color coordination so you remember where each of these rows are coming from, which is each of these linear equations, but that doesn't have too much of a bearing on how we label each of these when we're talking about row operations. So now, going back to this row operation, we are taking -3 times row 1 and adding it to row 3. So -3 times 1 is -3 plus 3 is 0. So we're going to have a 0 now in row 3. -3 times 1 is -3 plus 2. It's going to be a -1. -3 times 1 plus 1 is a -2. And then -3 times 0 plus 1 is actually just going to still be 1. So just keep that there. So then that's how we have just successfully done our third elementary row operation. So I bet you're wondering now, okay, so wait, why could we just do that? Like, that was totally crazy. But actually, if you remember back to our elimination method that we used to solve before we knew about matrices, linear system equations, we would multiply a row by a constant and add the two equations together to eliminate a variable. So that's just what we've done here. We just eliminated the x variable from the third equation by adding the first row times a constant to the third row. So pretty cool that we just eliminated our x value without even leaving the comfort of our own matrix. So these have been our 3 elementary row operations. I'm going to kind of leave you on a cliffhanger. You're going to have to watch the next video to see just how our elementary row operations can help us harness the power of matrices to solve for x, y, and z. So stay tuned and I'll see you next time.